evening, everybody, and thank you for the invitation and for the opportunity to share with you what we do at Zopa on a daily basis. Today I'm going to talk about the end-to-end process of creating a machine learning model to predict credit risk. And just to say a few words about me, I have a PhD in molecular biology, actually. I worked in neuroscience for like 8 years in University College London. And then I joined Zopa as part of the data science team, where I contribute to the generation of insights through machine learning and data analysis. And you may wonder, who is Zopa? Just in case you're not aware, Zopa is a digital finance company. In fact, it was the first peer-to-peer lending company in the world. It was created in 2004. And just to give you an idea of the scale that we're working at Zopa, since then we have lent more than £2 billion. We have more than 240,000 people have taken a loan from Zopa, and 60,000 people actively choose to invest their money with us up to date. So Zopa, as I said, is a peer-to-peer lending platform. So this means that we match people that want to invest their money with people that are looking to lend money to do something that they please. So one of the beauties of Zopa is that we have loans with lower rates for borrowers, and we provide higher returns to investors. So when an investor, I don't know if I can point here. It's not because it's pink. OK, so when an investor puts the money in Zopa, invests their money in Zopa, so what we do is we match it to borrowers that are looking for a loan, say to improve their house or to buy a car or anything like that. And when the borrower pays their money back into Zopa, we pass the capital and the interest back onto our investors. And by allowing this flow of money and by managing risk, we are able to provide lower rates to borrowers and higher returns to investors. But for this peer-to-peer lending model to exist, to be possible, at Zopa we have to manage all types of financial associated risk. And financial associated risk includes credit risk and fraud, and I'm going to talk about credit risk in a minute. But we also need to do ID verification. We need to do, for example, to detect if a document has been falsified. And we use machine learning to build all of our models and to basically make all of our decisions. And we also use machine learning for our marketing campaigns, for customer segmentation, and also pricing. And today I'm going to talk in particular about credit risk. So the first thing would be to know exactly what credit risk is. So in case you're not familiar with the term, credit risk is the risk of default on any acquired debt. So in other words, for us, it means the risk that one of the persons to whom we have lent money will not be able to pay us back. And we need to assess and manage risk for three main reasons. The first one is that we want to lend responsibly. So we don't want to lend money to people if that is going to hold them back, if that is going to affect their financial situation, say because, for example, they will not be able to repay their debt. We also want to manage risk because we don't want our investors to lose their money. So we want them to be confident that they will lend the money to people that will be able to repay back. And also because we want to keep our reputation as a prudential and responsible lender. So in order to build a credit risk model, we use machine learning, and we have to follow a series of steps. So today what I'm going to do is I'm going to talk about the entire journey of building a machine learning algorithm to predict credit risk. So in other words, the machine learning algorithm to predict or to attribute a probability to a person, to a borrower, to repay the debt that they will acquire from us. And this journey includes the first thing, that is gathering this data set, gathering the information, learning as much as we can about our borrowers. It also includes defining what risk is for us, which is basically what we want our models to predict. So in this case, is creating the target. Then usually I will show you that the variables are not as beautiful and ready to use as one would desire. So we have to do a variety of data cleaning and feature pre-processing in order for us to be able to use those variables in the machine learning algorithms. We also want to do some variable selection. We ideally don't want to use the entire data set. We want to use a little bit of that. And finally, we build the machine learning models. Which models do we build? How do they work? And finally, I'm going to talk about the research that we have done on model stacking. So the first thing, as I said, is to gather the data set, to learn about our borrowers. So how can we gather a data set? Where do we get it from? So Zopa, as many other financial institutions, get the information from credit agencies. Credit agencies are institutions that gather and store information about financial items of a variety of people. And the information, so basically they have information on as many credit items as you can imagine. For example, mortgages, current accounts, credit cards, also telecommunications. And the information that they have are, for example, the balances, so the money that the customer has on those accounts, whether the customer has made a payment or not, whether the customer has missed a payment or not. They also have aggregated views of those accounts. So for example, how many credit cards does the customer has, or how much is the total debt when we sum across all the credit cards that the customer has. And they also provide predictive variables. And they build these predictive variables on their own variables. And typically, they will use logistic regression. So institutions like us, like Zopa, what we use is we use a combination of their predictive variables with other variables and our own variables to basically improve the prediction on whether a customer will be able to repay the loan. So on top of the credit agency's data, we also have gathered information when the customer comes to our platform. So basically, this is information like, for example, what does the customer want the loan for? Is the customer self-employed? What's the salary? And that kind of thing. So just to give you a flavor of how big is our data set when we begin our journey, is we gather information for several hundred borrowers. And between the credit agencies, we use more than one, and our platform, we end up with something like 3,000 characteristics of our borrowers. So 3,000 different types of information, 3 different things about our borrowers. So the next step is to understand what risk is. So what are we going to predict? So this is creating the target. And this may seem trivial, but creating the target is actually one of the most important things, because if we have the wrong target, we may have the most predictive algorithm, but it's going to bring virtually no value to the business. So what do we define as risk? For us, risk is understanding whether our borrowers are in a financially difficult situation or if they are in a healthy financial situation. So what we do is we look at their financial items. So we look at the mortgages, the credit cards, the current accounts, and other financial items that each of our borrowers may have. And we look for signs of financial difficulty. And financial difficulty signs may be something like, for example, the customer defaulting on any one of those items, or also the customer missing payments, ideally more than 2, or also when the customer fails to pay the debt but doesn't default but goes somehow into arrangements with the entity that provided that debt. So all of those are signs of financial difficulty. So if we see that the borrowers have any of those signs, then we think that they are in a financially difficult situation, and in mathematical terms, we assign them a 0. If we don't see any of those signs, we conclude that the customer is in a financially healthy situation, and then we attribute them a 1. So now we have a binary target, so financially difficult situation or not, and this is what we're going to try to predict with our models. So by the end of this exercise, what we end up is with information from credit agencies, information that we collect at the time of the application, and the target, which is basically 0 or not, like is the customer at risk or not. And again, so it would be like several 100,000 borrowers, which are the rows of our data set, something like 3,000 characteristics, also known as features or variables, which are the columns of our data set, and one single target, which is a 1-0 binary target. So the next step is the feature or variable optimization, in other words, data cleaning and data preparation. So basically, it's about shaping up the data set so we can use it in our machine learning models. So there are mainly 2 types of variables. So we have categorical variables and numerical variables. I'm pretty sure you're all familiar with that. Numerical variables are variables that take a number. For example, salary can vary anything from 1,400 to 60,000 pounds. We also have categorical variables. So for example, city, where does the customer live? That would be something like London, Manchester, things like that. Each type of variable has a relatively different preprocessing. And what we encounter in these variables, the first thing and the most common is the absence of data. So this is what we call null values. So null values is when basically for a customer we have no information about that particular variable. Say for the variable number of credit cards and I am the borrower, then there's no information about whether I have credit cards or not. So what can we do with that? You may choose to basically remove all the data that is empty, but that would be removing pretty much the whole of your data. So ideally you want to replace that for something that you can actually use. So what can you do? For categorical variables, typically in machine learning, what you can do is to replace by some randomly extracted value from any other customer, right? So you take a sample from that same variable for other customer and you put it in the missing space. So that's one option. Another option that is also widely used is to replace it by the most frequency category. Like for example, if we're talking about the variable city, right, and I have customers that come from London, customers that come from Manchester, then I would replace, when I don't have information, by the most frequent category, that would be London in this case. In Zopa, we don't like doing any of that because we think that if the data is missing, it has to be for a reason. So what we do is we create an additional category that is called missing. So for the variable like postcode, it could be London, London, Manchester, missing, and so on. Another thing that can happen as well is to have rare values. So rare values, to continue with the example of postcode, is those labels that are very infrequently represented in your data set. So for example, you can think that because Manchester and London, they are very dense cities with a lot of population, most of our customers will come from those. But if you think about places like Brockenhurst, we would have a few customers that come from that place. So what happens is that the models tend to learn and think that every other customer that will come from Brockenhurst looks like that customer that saw in the data set. So then when we have a new customer, it will basically think that it looks like that and will make a very poor prediction. So that is what's called overfitting, right? When the model learns a lot about the customer that saw, but very little, but makes a poor judgment on the customer that is coming forward in the future. So in order to avoid overfitting, what we want to do is we want to replace rare values by something else. And again, the typical procedure involves replacing by a random sample from the same variable. It also involves replacing by the most frequency category. So every time a customer comes from Brockenhurst, we will now think that it comes from London. At Zopa, we don't like to do that. So what we do is to replace by an additional category that is called rare values. So we would have, every time that a customer comes from Brockenhurst or from another city that is very infrequently unrepresented, we would replace all of those by rare value. So where it said Brockenhurst, we would now say rare value. Where it said whatever Milton Keynes, they will now say rare value again. So that's about how we replace rare values. And then the final step that we need to do for labeled data, so categorical data, is to convert them into numbers somehow. We use scikit-learn as a tool to build our algorithms, and scikit-learn will not take any label in order to build the numbers, so we need to transform those categories into numbers. So how can we do that? Again, there are traditional methods. So for example, one of the traditional methods is to replace by the number of items in that category, or by the frequency if you want. So let's say that 60% of our customers come from London, so we would replace London by 0.6. If 30% of our customers come from Manchester, we can replace Manchester by 0.3. So that's a common procedure. Another common procedure is to assign some sort of order. If you have reasons to believe that your variable is ordinal, for example, days of the week, you can assign number 1 to Monday and number 7 to Sunday. So that's another valid procedure. Another valid procedure is one-hot encoding. So if you think of Titanic data set, one of the variables was male, female, or child. So from there, you generate two additional variables. So one is this female? So then you will have 1 or 0. And the second value is this a child? And then you will have 1 of 0. So that one works if you have a label as like a variable that has very few labels. If you have a variable that has a huge number of labels, like, for example, city, then you're basically increasing the size of your data set, so you may not choose to do something like that. And what we do at Zopa now is none of this. So what we do is we assign a value according to the target mean per category. So like, for example, going back to the postcode example, or city example. So I look at my category London, and then I look at my target. So how many or what percentage of the customers that come from London are in a good financial situation? 80%. So then I replace London by 80%. Then I will look at the label Manchester, and then I ask, how many of the customers that come from Manchester are in a good financial situation? 60%. So then I replace 60 every time I see Manchester. So when I do that, I am already adding some information to that variable. So that's another way of doing it, which is the one that we do at Zopa. For numerical variables, we have the same problems. We have null values, which is the absence of data. So there are traditional methods to fill in those values. So one of them would be to take a random sample of the data and fill in the empty value. Another method, which is similar to choosing the most frequent category, in this case would be to choose the mean or the median. Again, we don't think that this is the way forward, at least not for our data, because if the information is not there, it has to be for a reason. So what we do is we replace it by a number that is within the distribution of the variable, but quite far out. And the same is true for outliers. So outliers are values that are quite far in the distribution of the variable. So let's say if we're talking about a variable like salary, we can think that most of our customers are somewhere between 20K and 60K. So if a customer applies and claims that it earns 200K, we would call that an outlier. So how do we do that? To prevent overfitting, we are going to basically bring that value a little bit closer to the distribution. So if we think of a normal distribution and the outlier is here, we bring it a little bit closer. So we put it at the end of the distribution. So that's what we do at Zopa. And the final step is not so much about data cleaning, but about preparing our data sets for the machine learning models that we're going to use. So some models require that our features are squeezed between 0 and 1, or -1 and 1, or within that range. So what we can do is normalization, which basically is for each variable value, subtract the mean and divide by the standard deviation. That is one of the processes of normalization. And this is important for linear models, but it's also important for neural networks. And if we're thinking about building linear models, so linear models assume a linear relationship between your variable and your target. So what we have to do, in real life, most of your variables are not linearly related to your target. So what you want to do is to find some sort of linearization. So you can do that by applying a mathematical transformation, like, for example, logarithms, square roots, or any one that you like. What we like doing at Zopa is something that we have named rebinning. So what rebinning is trying to do is trying to capture the buckets that are linearly associated with the variable. So just to give you an example, so what we do is for each variable, we build a classification tree. So a classification tree will find the cats within that variable that group the customers within buckets that are either very likely to default or very unlikely to default, right? So then we replace those groups by the probability, and the probability basically is matching each bucket with how likely the customer it is to default. So then by ordering the buckets with the probability, we're discovering the underlying linear relationship, if any, between the variable and the target. And there is a blog coming up on this method very soon in Zopa, so if you're interested, you can stay tuned. And this is about it for preparing the data set. So now that we have prepared the data set, what we want to do is we want to do some sort of feature selection. So if you remember from previous slides, we start with around 3,000 variables from the credit agencies and from our platform. And ideally, we want to deploy a model that is about several tens of variables. And why do we want to do that? In general, less is more. So it's easier to implement. So it's easier for our developers to write code to call 50 inputs in order to score our customers than to write calls to gather 3,000 inputs to score our customers. So that's less work for our developers. And that is not just because we're good to our developers, but also it allows for less error, right? So the less variables you have, the less error, the less room for error that there is. The other important thing is that it's faster. So a model that analyzes and makes a decision on 50 scores, it runs much faster than a model that analyzes and makes a decision on 3,000 scores. And it's more reliable. Because just remember that we rely on third-party agencies. So if something goes wrong on their end, it affects our business as well. So the less variables that we use, the less likely we are to have an impact if they have an impact. So how do we go about to do some feature selection? There are a variety of methods available to do feature selection. So I'm going to describe what we have used in order to create our credit risk model. So in order to make quite a big jump from 3,000 variables to a few hundred of variables, so what we do is we look at the importance of these features, of each feature as attributed by random forest. Random forest assigns some importance to features based on how many trees in the forest have used that feature and how early in the survey the feature has been used. I will come back to that in a second. And then when we look at the importance, so every feature that the random forests have deemed unimportant, so basically that the importance is 0, we would remove from the data set. And we also analyze each single feature individually. So we build one classification tree versus the target for one feature, and we measure the predictive power. I'm going to describe how in a few slides. And if the feature proves predictive, we keep it. If the feature proves not better than the random decision, then we remove that feature. So by combining these two methods, we're able to pass from 3,000 variables to a few hundreds. And then when we have a few hundreds, in order to pass to a few tens, what we do is we allow the machine learning models to pick what works best for each of them in a process that is called recursive feature elimination. So what we do is like for each machine learning model, so logistic, regression, random forest, and XGB, so say we start with 300 features, just to give you an example, we build a model with 300 features, we analyze the performance. Then when we remove one feature, we build the model now with 299, we analyze the performance. If the performance is the same, then we can conclude that that feature is unimportant and we remove it. And we take the second feature and we analyze the performance, and on and on. So like if the performance drops a lot, then the feature is important, we keep it, we remove the third feature, and so on. So by the end of each exercise, we end up with a series of feature sets, each one selected by logistic, regression, random forest, and XGB. And it takes for one of our data scientists to decide basically which of those feature sets works the best. So this is how we end up with a few tens variables that we will use in our final machine learning models. So what are our machine learning models? What do we use to predict credit risk? So at Zopa, we like to build as many models as possible. So we use linear models, and we build logistic regression and multi-adaptive regressive splines. We also build 3 models, in particular random forest and gradient boosted trees. And we also build neural networks. So just to give you an intuition of how these models work, for those that are not familiar. So 3 methods are basically a series of yes/no questions that you make on your features. So for example, here we can ask a question to our customer, like, does this customer have a mortgage? If the answer is no, we take him through the right, and we ask the following question, does this customer earn more than 30K per year? If the answer is no, we take him again through the right branch of the tree, and we ask the following question, is like, do they live in London? This is all created data. This is not real, by the way. And if the customer doesn't live in London, then we can conclude that that customer is actually at a financially difficult situation. And if the answer to these questions are different, then we take them through other branches of the tree, and we can conclude different things. Depending on the combination of answers to our questions, we can conclude that the customer is more or less likely to be in a financially difficult situation. So this is the underlying of how a tree works, just to give an intuition. So random forest is actually a combination of these trees, and they are built using the same data set. So here we have like the several hundred thousands of customers. And the way you build a random forest is you extract a random sample of the data set and also a random sample of the features, 70% of the data set, and then you can extract as many features as you want. And you build a classification tree, number one. Then you extract another 70% of your data set and another subset of your features, and you build the second tree. And you repeat that on and on, typically between 400 times to 1,200 times. And so you end up with between 400 and 1,200 trees. And the beauty of these trees is that because they focus just on a proportion of the data set, on a proportion of the feature, they know a lot about that and not so much about the other features that they haven't seen. But then when you combine all of the trees, you basically have a better view of how your entire data set is behaving. So then what happens in random forest is that you basically measure the average probability of all these trees in order to make your decision. So this is pretty much how random forests work. And this is also pretty much like how gradient boosted trees work, with an additional difference that gradient boosted trees basically penalizes the wrong decisions that the previous tree made. So basically, the second tree is able to learn more about the mistakes that the previous tree made, and so on. So that's why, in general, gradient boosted trees are the best performing trees in the market. So then we have linear models, in particular logistic regression. So logistic regression is one step further on top of linear regression, if you want. So linear regression assumes a linear relationship between your target and your variable. So for example, we can think that the higher the salary of the customer, the more likely the customer is to be in a good financial situation. So that is what it would be represented in the plot 1. But then a linear regression outputs a series of variables. We actually want a yes-no answer, so we want a probability. So what we do is, like, to the result of the linear regression, we apply a logistic transformation that squeezes the values between 0 and 1, and then outputs the probability of the customer of being in a financially good situation given salary, for example. So by the end of the day, or by the end of the exercise, this model is able to assign a high probability to customers that can repay their loans and lower probability to customers that may encounter difficulties in repaying their loans. And this is the intuition of how logistic regression works. We can do an additional step. Logistic regressions are famous for behaving the worst out of the whole bunch of machine learning models that are available out there, but we can improve the performance of logistic regression by using a procedure that is called bugging of the predictors. Bugging of the predictors was described by Leo Bredman in the early 90s, and it's basically the same as what random forest is doing. So you extract a proportion of your data set, 70% of your data set, and you build a logistic regression, and then you do that again, you extract 70% of your data set, you build another logistic regression, and so on. And by doing this procedure, you end up with several different logistic regressions that focused on buckets of your data set. So then when you combine them all, you typically improve dramatically the probability, so the accuracy of the model at trying to predict whether a customer will be able to repay a loan. And here I put a thing that improves the ROC-AUC at the second decimal. If you are familiar with the ROC-AUC, like improving at the second decimal is actually quite a big improvement. We'll go back to the ROC-AUC in a minute. And another model that we have used in Zopa is neural networks. So neural networks, what they try to do is they try to mimic the neurons in the brain. So what they say about the brain is that one neuron, what it's doing is capturing inputs from all the surrounding neurons and then making a judgment, and then passes that judgment back onto another neuron. And the second neuron receives that input, but also receives input of other neurons that already made a judgment, and it has to make a second judgment based on the judgments of the previous neurons. So that is basically what a neural network is trying to do. So it's easier to understand if we go one neuron at a time. So you can think of each single neuron as a single logistic regression in the simplest terms. So this neuron here, what it does, it sees all the features of our data set, so like the few tens of features, and then it assigns a coefficient to those features, saying like the more of feature A, the more likely this customer is to be in a in a financially good situation, and the same for feature B, and the same for feature C, and then it squeezes the output of that linear regression with a logistic function, and it outputs a probability of repayment, a value between 0 and 1. And the other neurons in the first layer will do exactly the same. So all of them, the 3 neurons in the first layer, will have a judgment as to whether customer 1 will be able to repay a loan or not. And these 3 neurons pass their judgments onto the neuron in the second layer. So this neuron in the second layer is not longer looking at the features, it's looking at the judgments that the previous neurons have done. And again, it attributes a coefficient like judgment number 1. The higher the judgment of neuron 1, the more likely the customer is going to repay the loan, and so on for neuron 2 and neuron 3. And then it squeezes the value between 0 and 1 with a logistic transformation. And it passes the judgment onto the third layer in forms of a probability, in forms of a value between 0 and 1. And so do the other neurons in the same layer. So all of them will make a judgment, measuring the judgments that were made by the neuron in the first layer. And the third neuron of the third layer will basically make the judgment or the judgment and will output in a similar way the final probability of repayment. And by doing that, what basically the neuronal network is enabling us to do is to capture the interactions between the variables that are present in the data set. Because neuron number 1 captures some sort of the interaction, neuron number 2 will capture a different sort of interaction, and they pass their judgments onto neuron on the second layer, and the second layer makes a reinterpretation of the data, and so on. So basically, what they say about neuronal networks is that they are able to mimic any potential function that maps your features to the target that you want to predict. So this is the beauty about neural networks, and also that you have to do very little feature engineering. And finally, once we build all our models, we need to assess how good they are at making the predictions. So what we use at Zopa is the ROC AUC. The ROC AUC allows us to say for each threshold of the probability, so the model outputs a probability between 0 and 1. So if I choose a threshold of 0.5, how many times did the model make a good judgment, as in how many of our healthy customers did it select as healthy? And for that same threshold, how many times the model got it wrong? And then we move it to another threshold, 0.8, and then again, so if the probability threshold is 0.8, how many times the model made a good judgment versus how many times it made the wrong judgment. So what you want to do is you want to have a value of the ROC AUC close to 1 as much as possible. So that's the best case scenario in which your model always gets it right and never gets it wrong. So what we do next is basically pick the one that is best based on the highest value of the ROC AUC. And finally, we do something that is called model stacking. So model stacking is basically putting a lot of models together and evaluating or generating a new model that considers the outputs of all the previous models. So in this case here, so we have built a series of models. We built logistic regression, we built random forest, gradient boosted tree, neural networks, we built Mars on the same data set. All of them will have a probability. And then with those probabilities, we want to do something. We want to evaluate how, or the combination, what combination works best. In the simplest of scenarios, what we can do is we can average the probability of all of them. And instead of considering one model, we just consider the average of all the models. So that's one way of stacking algorithms. Another way of stacking algorithms is to build a any machine learning model that you want, using the probabilities of the first models as the variables. So you will have a machine learning model on top of the other machine learning models. And that output produced by that meta model is what you can use then to predict the probability of repayment. So what we have found at Zopa, unsurprisingly, is that gradient boosted trees and neuronal networks are the ones that produce the best predictions. And this is basically what you can see in any Kaggle competition and any other data set contest out there. And then when we do analysis, like if we combine the probability of gradient boosted trees with neuronal networks, we actually manage to improve the accuracy of the model. So like the model that averages the two probabilities outperforms each one of the two individual models. So this is what we actually chose to use for our next credit risk scorecard. And we also built a variety of learning algorithms on top of the on top of the 5 models that we have on the left. But we have seen that it doesn't really improve our performance quite dramatically. So it doesn't really make business improvement big enough to justify the deployment of such a complex model. And the reason being, potentially, is that all these algorithms are relatively similar. They're quite correlated among themselves. So by the end of this exercise, so we end up with a data set that is clean, able to be used in a machine learning model that contains a few tens of variables out of the initial 3,000 variables. We have built and selected the 2 best performing algorithms, and we combine the probability of the 2 of them in order to determine whether our customer is in a financially difficult situation or not. So in other words, whether a customer, or how likely our customer is to repay the loan if we were to give money to them. So I hope I could give you a flavor of how we work at Zopa, and thank you for your attention.